Hello students. So today in Disconnection Approach, I will tell you the use of aliphatic nitro compounds in the retrosynthetic analysis of some amines and some keto compounds. So before discussing the retrosynthetic analysis of amines and keto compound via nitro compounds, we should know some of the general reactions of this nitro compound. For example, if we have RNO2, then it can be reduced into amine. Okay, in presence of the reduction can be done. Okay, so this is all the reduction can be done in presence of lithium aluminum hydride. Now suppose if you have this one, this NO2 is attached to the secondary carbon. In this case, in presence of TiCl3, it may give you the ketone. So if target molecule is amine, then that can be interconverted into nitro group. In the same way, if target compound is keto, then that can be interconverted into nitro compound via FGI. Now suppose if you have CH3NO2, then this in presence of any base, it can abstract this acidic hydrogen. So the hydrogen which is present in this CH3 is acidic because it is attached to one of the electron withdrawing group. NO2 is the electron withdrawing group. So that's why this base, it can easily abstract this acidic hydrogen from the CH3 and it will give you okay. Now this in presence of alkyl bromide. So now this can act as a nucleophile and it may give you the SN2 reaction to give you okay. Now this can further be reduced into the this amine. So this is one of the reaction that may occur. Now in the same way, this may further reduced now this CH3, this nitro compound, may react with aldehyde to give alpha beta unsaturated aldehyde. This can also be obtained. Okay, so if we have alpha beta unsaturated nitro compound, then that can be converted into this two reactant molecule. One is this nitro and another is aldehyde. So if we have this target molecule, and this target molecule that can be interconverted via FGI into this nitro compound, and this means if we can give a disconnection over here and you will get these two nitro compound. It is nitro compound and aldehyde. Now you can see the mechanism. If I write the mechanism for this, then how it occurs. You can see now this nitro compound in presence of base, it is giving you this nucleophile. So this is the nucleophile that I am writing. Okay. Now this nucleophile, this will attack over the aldehyde. Now this can also be written in a resonance stabilized form, and I can write it the resonance stabilized form of this, that is this is the resonance stabilized form. Now in presence of this aldehyde, suppose I have aldehyde CH3 CHO, okay, or I may write, suppose I have this carbonyl compound. So this nucleophile will attack over here, and it will give you okay. Now in next step, you may write, after this esterification, now in next step it will undergo dehydration to give you this alpha beta unsaturated nitro compound. Okay, so this is the mechanism for this. By mechanism it will be more clear. So how we can convert this alpha beta nitro compound into these two reactant molecules. So these reactions should keep in mind while writing the retrosynthetic analysis of amine and keto compound via nitro compound. Okay, let's take the example of some amines. Now, let's take one of the example. Okay, so I have taken, suppose, this example. Okay, so this is the target molecule. This is your target molecule. Now, this target molecule, it can be broken. It can be broken from where you should break it. Now, as I told you, this amine, it can easily be converted into the nitro compound via FGI. So amine that should be converted into the nitro compound. I am writing here FGI, and that can be written okay, R1, R2, NO2. Now in next step, so this is, here you can write the reduction, below the arrow you can write the reduction. Now you will disconnect it. Now from where you will disconnect it? No doubt we should disconnect it. We will not disconnect it from here. We should disconnect it, and we will not disconnect it from here also. Okay, so no, this non-nitro, N has the positive charge, so this will have the negative charge. Okay, this will have the positive charge, and like this. Okay, so we know some of the reactions of this nitro compound. So we should disconnect it from here. Suppose I am disconnecting it from here. Then, keeping in mind these reactions, what you can write? You can write the synthon that you will get, one of the synthon. So over here you can write the Cl minus. Over here you can write the Cl. So this is one of the reactant molecule, and another reactant molecule. This is another reactant molecule for this. Minus charge is here. Then you will write. Suppose this is your So minus, you will write the H plus. So these two are the synthetic equivalent which is obtained from here. So this is reactant 1 and this is the another. We can write the synthesis from here. We can write the synthesis directly. We can write the synthesis. So one of the H is present over here, and removing this H with the help of base generates a nucleophile, and this nucleophile can attack over this carbon and the chlorine will leak out. So if I write the synthesis, then first of all I have this nitro compound. This in presence of base, so this will give you now so what you will get, R1, R2, and this may undergo reduction to give you the target molecule. Okay, so the amine synthesis can be done using this nitro compound. Now let's take another example. Now suppose if you have a keto compound, suppose I have this keto compound. Suppose I have this keto compound, then how can we disconnect it? Okay, so now if you will see, then this is the cyclohexene, and I have already discussed the retrosynthetic analysis of alkene or the cycloalkenes, in which if we have the cyclohexene, then it can be disconnected via this FGI and it can be converted into the Diels-Eder reactant like the butadiene, the diene and dinophile. Now, so now as this is the keto one, so this keto compound we can do the FGI. So we can do the FGI, and I can write it here FGI, and I will write here NO2. Okay. Now, what is the reason of writing here NO2? Because this is a cyclohexene. Now, after writing after converting into this diene and dinophile, then this dinophile, all of you know, this dinophile, it should have a electron withdrawing group. Okay, it should have the electron withdrawing group. So that's why this FGI is done. So I have given a electron withdrawing group over here, and so in presence of this electron withdrawing group, the dinophile can easily react to the diene. Okay, so that's why this is the reason that here this FGI is done and it is converted into this NO2 group. Now we can again do the FGI. Now we should do the Diels-Eder reaction. So you can do, okay, so what you will get diene and plus this dinophile. This is your dinophile. Now as you can see here, we have one of the electron withdrawing group. So due to the presence of electron withdrawing group in Diels-Eder reaction, the diene should be electron rich, whereas the dinophile should be electron deficient. So this NO2 group here, it will make this dinophile electron withdrawing. Now we can again do the FGI. So already I have told you, if we have alpha beta unsaturated nitro compound, that it can further be disconnected to give a simpler reactant molecule. So this can give you the simpler reactant molecule, further FGI. So we will get one of the aldehyde and another this nitro compound. Okay, now we have found the simpler synthetic equivalents, and using this synthetic equivalent, first of all react this. You have to go in a backward direction. React this, you will find one of this alpha beta nitro compound, and this will act as a dienophile. It will react with this diene to give this one, and further FGI will give you this. Further reaction with TiCl3 will give you this. Okay, so you can write the synthesis now. You can write the synthesis easily. So first of all, we have this CH3NO2, this in presence of base, this will generate a nucleophile. This nucleophile in presence of aldehyde, this will generate a alpha beta unsaturated nitro compound. Okay. Now this will act as a dienophile, or we can write it as this way. Now this will react with a diene to give you and this in presence of TiCl3, this will give you the target molecule. Okay, so hope all of you are clear here. So using these reactions, we can write the retrosynthetic analysis of this amine or this keto compound. So if we have a keto compound, then we should follow this reaction. If we have an amine compound, to write the retrosynthetic analysis of amine compound, we should follow this reaction. Okay, now let's see another example. Okay. Now suppose if you have this one, and you have to write the retrosynthetic analysis of this. Now this is 6-membered ring, and first of all we can see it can be, if we want to disconnect it, then that can be converted into the alkene molecule, so that the further disconnection give you the diene and dienophile. So that can be converted into alkene molecule via FGI. I can write it. This will give a double bond over here. So this alkene, on reduction, it will give you this target molecule. Okay, now you have this one and this two. Okay, now on further FGI, so I can write it in a simpler starting material. Okay. So amine on reaction with aldehyde, it will give you the imine on reduction, that will give you this amine. Okay, so that's why this FGI is done. So first of all, this amine and this, it will it will react to give you the, suppose, so here I have now let's take another example. Suppose we have a target molecule. This is your target molecule. This is the target molecule. Now if you want to disconnect it, okay, so this is now this target molecule, this can be obtained from this part and this part. It can be obtained from diene and dienophile, so that can be converted into one of the alkene molecule. So if I do this FGI, then I can write, or I can convert it into here double bond. So this one reduction, so this double bond will get reduced into this one, and now further this can be disconnected. Further this can be disconnected and it can be written into more simpler molecule. So aldehyde and this amine undergo condensation reaction to give the imine, and imine after reduction we will get this amine compound. Okay. Now you can see if you do the disconnection of this into diene and dienophile, then diene will not have this electron withdrawing group. So dienophile. So dienophile should have the electron withdrawing group. That's why this NH2 can be converted into the electron withdrawing group. So further you will do the further FGI, and we can write NO2 now. Now this can undergo the further functional group interconversion, Diels-Alder reaction. So one of it can be, so this we can write okay. Now this can be written in this way also. Better to write it. Sorry. Like this. Now all of you know this can further be disconnected using this reaction. This can further disconnected, and you can get here so these are the much simpler reactant molecule. Now from here we will get in a reverse direction and we can get the target molecule. So if I write the synthesis of this, then you can see the synthesis. I can rub this part. If I write the synthesis, then you can see, first of all, using this, I have this nitro compound, and in presence of base it will generate a nucleophile. This will attack over benzaldehyde, and you will get alpha beta unsaturated. Finally you will get alpha beta unsaturated nitro compound is in presence of this diene, or better to write. Okay, so you will get your Clear? Now this can be, reduction will take place. On reduction that can give you this nitro group undergo reduction, and you will get here pH and H2. Further, in presence of this esteraldehyde, the condensation reaction will occur between this aldehyde and this amine to give you the imine functional group. So I can write here imine functional group, N double bond CH, CH3. So this can undergo reduction. To give you now you have got this one, and further reduction that will give you the target molecule. Further reduction that will give you the target molecule. So these are some of the examples for writing the retrosynthetic analysis of amine and a keto compound via nitro compound. Thank you.